In this video, we're going to begin Chapter 2, Single Degree of Freedom Systems. And here we're going to focus just on Section 2.1, Undamped Single Degree of Freedom Systems, or SDOF systems. So undamped single degree of freedom systems are the simplest of all vibration systems. Only a single coordinate is necessary to completely describe the motion. Now, many different coordinates can be used, but there is typically a best choice for the coordinate. These systems consist of an inertial element oscillating about an equilibrium position. And these systems consist of a transfer of kinetic to potential energy and back again, indefinitely with no damping. So here we're talking about undamped systems. So this continues forever without any damping. Now we can have rotational, translational, or torsional systems. So for example, a rotational system might be like a pendulum, where we have this mass of rotating around some point. So you can see here our coordinate that we can choose is theta. Translational systems are, for example, like a mass and a linear spring. And here the coordinate that we might choose would be x, describing the translational motion of the mass. And we can have torsional systems where in this case we would have this disk kind of rotating under torsion, where here we could use theta to describe that, that motion. All of these are examples of single degree of freedom systems. So a simple translational vibratory system is the easiest to deal with initially. So in this case, we have a perfectly rigid mass of value m is attached to a rigid support. So this is a fixed support here by a spring with an unstretched length of L naught. So this is the unstretched length of this spring, and a spring constant of K. So this describes the stiffness of the spring. Now there are many coordinate systems that we could use to set up this problem. So for example, we could choose to describe the position of the mass as by the coordinate x1, so the distance from this fixed end. We could choose to use x2, so the distance from, say, another end. Or we could choose to use x, which would be the distance from the equilibrium position. So if this is the unstretched length of the spring, L naught, the mass would be in equilibrium when it's at, when the spring has the current length of L naught, and so the distance x here is the distance away from that equilibrium position. So we could use any of these coordinates to describe this motion, and we only need one to completely describe it. As we'll see, there is a great advantage to choosing the equilibrium position as our base coordinate. So in this case, this would be x here. So once we've chosen our coordinate, we can then start to write our equations of motion. So we begin with the free body diagram and mass acceleration diagram of our mass, of our system, with the mass displaced in the positive coordinate direction. So we chose our coordinate, we're going to use x in this case. We choose the positive direction, so we assume that to the right is positive. And then we draw our free body diagram, so this is our free body diagram, and our mass acceleration diagram, with the mass displaced in that positive coordinate direction. So once you've chosen a positive direction, everything must remain consistent with this choice. It's very important that once you choose your positive coordinate direction when you draw your diagrams, and then once you choose that, you keep that for the whole analysis procedure. So you can see if we displace the mass to the right, we have these forces acting on it. So the spring force is acting to the left, acting to kind of restore that, and the value of the force in the spring is kx. We also have, in this case, the mass was sitting on the ground, so we have the weight of the mass, mg, and we have the normal force, n. And then its motion is restricted to the horizontal direction, so the acceleration of this mass is in the positive coordinate direction, which is to the right. So we have the acceleration as mx double dot. Now, because there's no acceleration in the vertical direction, the mass is just supported on these rollers, mg equals n, and the acceleration is only in the positive x direction. So it's just in this direction. And we have no acceleration vertically in this case because it was supported. So mg is just equal to n. So we can write the sum of the forces in the horizontal direction. To the right is positive. So sum of F is equal to mx double dot. So our sum of F is equal to minus kx, and the acceleration is mx double dot. So this is our equation of motion. So again, if we write our Newton's laws, sum of F is equal to ma, so minus kx is equal to mx double dot. So we can rearrange this to bring everything to the right hand or the left hand side of the equation. So mx double dot plus kx is equal to 0. We can then divide by m to get x double dot plus k over mx is equal to 0. Now we can define this quantity, this k over m, we can call this p squared. And then we can write our equation as x double dot plus p squared x is equal to 0. And this is the standard form of the equation of motion, where p is equal to the square root of k over m, and is equal to the natural frequency of the system. Now it's important to make a note about the notation here. So most texts actually use omega n to represent the natural frequency. Here we use p, but you may encounter omega n in other texts, and it is equivalent. We just use p in this lecture series as well as the online notes. So now we've got this standard form of our equation of motion. X double dot plus p squared x is equal to 0. So this is the standard form of an undamped single degree of freedom system for free vibration. So this equation is a second order ordinary differential equation with constant coefficients. So we can use familiar solution techniques to be able to solve this. And what we really want to find is the value of x as a function of time. So we can assume that this equation has a solution of the form x of t is equal to c e to the st. So now x dot of t is equal to c s e to the st. X double dot of t is c s squared e to the st. So if we plug those in to our equation, x double dot plus px squared is equal to 0. This becomes the equation, the expression shown here. So we're just plugging in x as well as x double dot into this equation. We can divide by c e to the power st. And we get s squared plus p squared is equal to 0, which has roots s is equal to plus or minus ip. So the solution to our equation becomes the expression shown here. So x of t is equal to c1 e to the power ipt plus c2 e to the power negative ipt, where c1 and c2 must be allowed to be complex numbers in this case. To proceed, we make use of Euler's identity. So you may recall Euler's identity, which is shown here. E to the I phi is equal to cosine phi plus I sine phi. And so in this case, e to the ipt is equivalently equal to cosine pt plus I sine pt, and e to the minus ipt is cosine pt minus I sine pt. And that comes from the unit circle shown here in the real and imaginary space. So using the Euler's identity and recalling our equation, we can replace these exponential values with cosine and sine terms. And we can collect like terms. So we've got a cosine pt here and a cosine pt here. So we can collect the coefficients out in front of that. So c1 plus c2 cosine pt. We've got an I sine pt here and an I sine pt here. So collect the coefficients in front of that. We get c1 minus c2. And now we can define two different constants. So we can say that a is equal to c1 minus c2i and b is equal to c1 plus c2. And then we can, to replace those into this equation here, we get this expression here. So x of t is equal to a sine pt plus b cosine pt. And this is the standard form of the solution to this equation. So it's the general solution to x double dot plus p squared x equals 0 and is the free undamped vibration response to a single degree of freedom system. So we can see that the response is simple harmonic motion, which occurs at a frequency of p. So the frequency in the response here is p, which is the natural frequency of the system. And we see that it's a simple harmonic motion. So for the simple spring mass system that we're considering, we know that P is equal to the square root of K over M. So the natural frequency is a fundamental property of the vibrating system. So it doesn't change depending on the initial conditions or anything like that. It is a fundamental property of the system that is related to its stiffness and mass properties. It's important to note that P is measured, or the natural frequency is measured in units of radians per second. So if you encounter a problem with Hertz or RPM, then you need to do some conversions to make sure that we know that P is measured in radians per second. So we've got these two constants, A and B, in our solution response here. So A and B can be determined from the initial conditions of the system. So typically we'll define initial conditions as the initial position, so x at time 0, and the initial velocity, so x dot at time 0. So at time t equals 0, x of 0 is equal to x naught, and x dot of 0 is equal to v naught. So these could be given or known quantities. So from the first one, we can plug this in. So this is, so x of 0, so when t is equal to 0, we plug in that here, t is equal to 0, t is equal to 0. So the sine 0 goes to 0, cosine 0 goes to 1. So b is equal to x naught. And then from our velocity equation, x dot of 0, again, sine 0 goes to 0, cosine 0 goes to 1. And we see that a is equal to v naught over p. So the response of the system is given by the expression here. So x of t is equal to v naught over p sine pt plus x naught cosine pt. And this completely specifies the response for all time greater than 0, given the initial conditions and the natural frequency of the system. Now there are other forms of the general response. So as an alternative to this equation, we can write out the solution in a different way. So we could write the response as x of t is equal to x sine pt plus phi, where x is equal to the square root of x naught squared plus v naught over p squared, and phi is equal to inverse tan of x over v naught p. We can also write it as x of t is equal to x cosine pt minus alpha, where x is the same in this case and alpha is given by the expression shown here, where you can see that alpha plus phi is equal to 90 degrees. So the x here is called the amplitude, and the alpha or the phi is called the phase angle. So as an aside, we can see how these things are, how we kind of came to these expressions by looking at our trigonometric identities. So if we have an equation like this, x sine theta plus phi, from our trig identities, we can write that as shown here. If we say, in this case, theta is equal to pt, then x sine pt plus phi is equal to this expression. If we let a is equal to x cosine phi and b is equal to x sine phi, then we can write that as shown here. And a squared plus b squared is equal to this expression, which we can simplify or rearrange. This goes to 1. Cosine squared phi plus sine squared phi is equal to 1. So a squared plus b squared is just equal to x squared. So that we see that x is equal to the square root of a squared plus b squared. And the angle phi is, so tan phi is equal to sine phi over cos phi, which sine phi we had defined as from here. And cosine phi we can see we get from here. And so tan phi is just equal to b over a. So that means that phi is equal to tan inverse of b over a. So you can see, if you kind of relate that back to what we had on the previous slide, you can see how those quantities are equivalent in the representation of the general response. So this is what the general response looks like. So we get this simple harmonic motion. So we have this sine and cosine form. So x naught describes the initial position. So this is a graph of x of t versus time. So x naught is this initial position. V naught is the slope, so our initial velocity. And then these, the phase angle can be kind of graphically shown here. The period of the response is shown here, which is related to the natural frequency, as the period is equal to 2 pi over p. And the amplitude is depicted here. So the period tau is the time required for our harmonic motion to repeat itself. So it's related to the natural frequency as this. So p tau is equal to 2 pi. So tau is equal to 2 pi over p, or p is equal to 2 pi over tau. So this just relates the period and the frequency of a harmonic motion. Another common unit for measurement of frequency is in cycles per second, or hertz, of a particular harmonic motion. Since there are 2 pi radians per complete cycle, we can note that the frequency in hertz is just 1 over tau, which is p over 2 pi. So we quite often have to convert between radians per second and hertz, so this is a useful relation. Now we can also think of the response of the undamped single degree of freedom system in terms of rotating vectors. So if we consider two vectors with magnitudes a and b that are fixed 90 degrees apart, rotating with an angular velocity of p, as shown here. So these are rotating in this direction with an angular velocity of p. Now the vector sum of a and b is another vector with x with the magnitude of square root of a squared plus b squared. So x, the magnitude of this one is going to be the square root of a squared plus b squared. This we do this this vector sum. And we can see that the angle between a and x is equal to inverse tan of b over a, which is phi. We can also see that the angle between b and x is alpha here, which is the inverse tan of a over b. So now, if we let b is equal to x naught and a is equal to v naught over p, the response x, or the position x of t, can be interpreted as the vertical component of the rotating vector x. So this is our vector x. It's rotating counterclockwise in this direction. So the height here, this position, as that position changes over time while this is rotating, the vertical component of that can be interpreted as x of t. So you can see that from the figure here that this is equal to a sine pt, which is this height, or v naught sine pt, plus b cosine pt, which is this height, or x naught cosine pt. So x of t is equal to v naught over p sine pt plus x naught cosine pt, which is the result that we arrived at before. So we can also see that x of t is equal to the vertical component of this triangle highlighted here, so which is x, this magnitude, sine pt plus phi. So this angle here is pt plus phi. So you can see that this is the height of that can be also written in that way. Alternatively, this height can be would be equal to x cosine pt minus alpha. So looking at this vertical component here, so this whole angle is alpha. This angle here is pt. So this angle is alpha minus pt. So if we write this as x cosine pt minus alpha, noting that the cosine of pt minus alpha is equal to the cosine of alpha minus pt. So those things are equivalent. So you can see, again, that these are all equivalent and can be thought of as kind of the vertical component of the position of this point as this vector rotates around. Now, another approach that we can use is using energy methods. So if the system is undamped, there's no energy loss, and the total mechanical energy, which is the kinetic plus the potential energy, is conserved. So it's a conservative system. In a system like this, we can use something that's called the energy method. So basically, we're saying that the T plus U is a constant. So T is the kinetic energy and U is the potential energy. The total amount of this is a constant in a conservative system. And the energy is just converted from T to U throughout the time. So again, T is the kinetic energy and U is the potential energy. So this means if the sum of these is a constant, this means that the derivative of T plus U is equal to 0. So we can use these properties to determine the equation of motion for a conservative system. So let's consider our spring mass system that we talked about earlier. The potential energy that can be stored in this system is, at some displacement x, is U is equal to 1/2 kx squared. So this is the potential energy stored in the spring. And the kinetic energy of the system is given by the motion of the mass. So T is equal to 1/2 mv squared, or 1/2 mx dot squared. So our kinetic plus our potential energy is a constant, so 1/2 mx dot squared plus 1/2 kx squared is equal to a constant. Now, if we differentiate with respect to time, this derivative here becomes this expression, so we end up with x dot mx double dot plus kx is equal to 0. And this must hold for all times t and all velocities x dot. So it must always be true. So since x dot is not always equal to 0, that means that this term must be always equal to 0. So for every time, mx double dot plus kx is equal to 0 at all times t. So this is familiar from our earlier efforts to define the system. So again, we arrive at the same equation of motion. Instead of using Newton's laws, in this case, we use the energy method. So if we can assume a conservative system with 0 potential energy at the equilibrium position, then we can say that Tmax is equal to Umax. So the maximum kinetic energy in the system is equal to the maximum potential energy in the system. So they're just converted from one to the other. So at the equilibrium position, there's zero potential energy. It's all kinetic energy. And at the other sort of limits of the motion, where the kinetic energy is equal to zero, the potential energy is at a maximum. So the response of our system is x is equal to x sine pt plus phi. So the maximum that this can be is when sine is 1. So the maximum this could be is x. So it means the maximum potential energy would be 1/2 kx squared. The velocity would be given by the expression here, and the maximum that this can be is when cosine is 1. So the maximum that this could be is, the maximum velocity would be px, so the maximum kinetic energy would be 1/2 m px squared. If we can say this, if we have this conservative system with zero potential energy at the equilibrium position, so we know Tmax is equal to Umax, these two quantities are equal to each other. So we can simplify this, and we can see that we get p squared is equal to k over m. So we arrive at the same expression for the natural frequency using the energy method approach. So p is equal to square root of k over m. So this approach is known as Rayleigh's method, and we will encounter variations of this later in the course. It's important to note that this approach is limited to conservative systems which have zero potential energy at the equilibrium position. But when we have that type of a system, this is another approach to come up with the expression for the natural frequency.